Good morning, everyone. Hope you're doing all right today. What am I doing here? Share screen. Do you guys ever get on like a real, like you're sure you're right and you get on a really high, like moral high horse only to be shot down like 2 seconds later? That totally happened to me this morning. I was in the Zoom meeting and nobody was here. And I was like, what is going on? Where are my students? They're taking off early because it's spring break. Where are they? And then I realized I was in the wrong class and I was in my Chem 130. So you guys are great. And I totally got shot down. And I think that's a good thing. We should all get shot down every now and then. That was seriously, I was like, where are they? Where are they? Okay, so let's finish up chapter 7 here on chemical equations. Hopefully right now we're, good-ish on balancing chemical equations. You got to do some practice on your own, but we've done the first part. Now we're going to talk about like different types of chemical equations. So we had first talked, we're kind of exploring this idea of a precipitate reaction. And so a precipitate reaction is when you have two things that are aqueous or soluble. We mix them together and then all of a sudden something solid forms. And so this is a great example up here of a precipitate reaction. Do I expect you to have every precipitate reaction memorized? No. But you do want to be able to identify them. It would look something like this. So an aqueous thing mixes with an aqueous thing to form one or more solids. How would you know that this is a solid? Well, you would have to look at those solubility charts, so this is kind of what's going on. So before we mix, we have a solution over here of Ki, and Ki are aqueous, meaning that once they go in water, they dissociate. The bond between the two of them isn't that strong. It's actually weak enough for the polarity of water to pull it apart. So they're by themselves. Then over here in another container, I've got lead to nitrate. And the lead and the nitrate are also not connected strong enough that the water can't pull them apart. So we've got two separate containers where these things are just sort of all floating around. Well, what happens when I pour them together is that now we've got a couple different possibilities as far as what can come together, right? When they were separated here, it was only K and I that could get together, and it was only lead and nitrate that could get together. But when we mix them together, there's some new possibilities, right? We've got K and I that could potentially get back together, but we've already established Ki as aqueous, right? So I know that they're not going to get together. It's kind of like, like all these people have broken up and gone to a party. All right. K and I aren't getting back together, and lead and nitrate aren't getting back together. But because they're all in the room together, now potassium can take a peek at nitrate and is like, oh, hey, nitrate, how are you doing? Let's try it out. So they try and, get together, and that bond is also relatively weak. So they stay aqueous. But there is a magic combination in the room, and that is between the lead that now has access to the iodine. And when these two things get together, their bond is so strong that they will precipitate out. It is stronger than the force of the water's pull. So we get a couple here. And when predicting what the possible combinations are, you can kind of think of this as like a swingers party, right? There's a bunch of couples that all get mixed together and they're swapping partners, all right? But they're only going to go metal, non-metal combination. We're never going to go metal, metal combination or non-metal, non-metal. So you aren't going to combine the potassium with the lead, all right? That's never going to happen. And you're never going to combine the iodine with the nitrate. You have to flip-flop metals and non-metals. So when trying to figure out what the potential products are, take the metal from the first one and combine it. Metal from the first one, combine it with the non-metal from the second, and then the metal from the second and the non-metal from the first. Or outsides and insides. Okay, those are going to be your possibilities. So when looking at this formula here, the potential insoluble products are these two. Now, how do you determine if these are insoluble? You would have to go to the solubility chart. All right, so you'd have to go and look and see, oh, what happens with potassium? Well, I know for a fact potassium and nitrate are always soluble in water, so this is not going to be a precipitate. Lead and iodine, that is kind of a magic combination where we would get a precipitate. Again, I wouldn't expect you to have those solubility charts memorized, right? Even when you're doing homework and stuff, you will just need to be able to reference it. So this ends up being our insoluble product. And so now we know that we have a precipitate reaction. So we mixed everything together, and the lead and the iodine have a really strong bond. They are forming a couple here. They're solid. So when writing equations for precipitate reactions, you flip-flop the metal with the non-metal. You make sure that the new products are charge neutral with whatever the charges are on the original guys. And then you balance the equation and you reference the solubility charts. So right now, what I want you to do, I just want you to tell me what the possible or the potential products are for these two things. So I've got sodium carbonate, and it's combining with, I'm not going to say what it is because I want you to figure out what the charge is on it, but we've got this thing over here, CuCl2. So I want you to flip-flop partners. Tell me what the two products are. If you want to go a step further and like reference the solubility charts, you can to tell me which one is the precipitate, but we'll start there. Okay, so when flip-flopping these, we're going to take the hello, there I am. Okay, we're going to take the sodium and combine it with the chlorine. So that one's easy, right? That's just sodium chloride, NaCl. This copper and this carbonate, we need to flip-flop. Copper in this case has a 2+ charge, and carbonate always has a 2- charge. So it would just be CuCO3. So these should be our two possible insoluble products. I will tell you right now, this is definitely soluble, right? Anytime you throw salt into water, it dissolves unless it's saturated. The other one is a insoluble product. So that is going to be our precipitate. Important thing to do at the very end. So, also, if for whatever reason the two products were both aqueous, like you didn't get a precipitate from either of them, you would just put an arrow and you'd write no reaction. Okay, the no reaction because nothing's happening. But in this case, we do have a reaction. And then, so we do have a precipitate. We want to balance the equation. That's the last thing that you want to do here. So we're going to throw a 2 in front of the sodium chloride just to get the right number of atoms on both sides. So it's not too bad, right? I think the one thing that I see happen is people will combine the two metals together, or they'll combine the two nonmetals together because they don't have a great understanding of what an ionic compound is. Remember, ionic is a metal and a nonmetal. Your product also needs to be a metal and a nonmetal. So just make sure you're only going outsides and insides. So these equations that you're seeing right here, this is known as a molecular equation. And when I write a molecular equation, it's where everything has the neutral chemical formulas. So do you see how everything is coupled together like this? And there's no charge in the upper right-hand corner on these. Why is there no charge? Because they're all bonded. So their positive and negative charges are good. But this little aqueous thing is telling me, that's signaling to the reader that these are actually broken apart. Like we're delivering this as a solution. So those two things are not actually connected. So in the molecular equation, you do write everything coupled together. You put the aqueuses there to let the reader know that they aren't actually, in solid form, that they're floating around. This is probably the easiest equation to write. The next equation is called a complete ionic equation. Sometimes I call this the complete pain in the butt equation because it's really cumbersome to write out. But what you do in a complete ionic equation is anything that's aqueous, you're going to break apart into its ions. So in this initial equation here, I would break this thing up, I'd break this thing up, and I'd break this thing up into its ions. I would keep the thing that's solid intact because it isn't going to break apart into ions, right? So if we look here, I've got silver nitrate. So I'm going to break that up into the silver and the nitrate. So here's the silver, Ag+, and you write a little aqueous. Here's the nitrate, NO3-, and you write aqueous. Sodium chloride breaks apart into an Na+ and a Cl-. And then I also need to break apart this thing over here, Na+ and NO3-. There's the arrow right there. So it's like, it's a lot of it's a lot of characters to write out. You do need to know how to do that though. Important thing though, when writing a complete ionic equation, separate only aqueous things. Don't separate anything that's a solid, a liquid, or a gas. So if you see any of those symbols, you keep those things intact. The final equation that we have is what's known as the net ionic equation. And here's the complete ionic equation. Do you guys see how there are a couple things that are the same on both sides? Like here I've got NO3- as an ion, and here I have NO3- as an ion. And here I have Na+ and Na+. Those are what are called spectator ions. It means that they are delivering the important stuff, but they're not involved in the reaction themselves. So this NO3- kind of just delivered the silver, and this Na+ sort of just delivered the chlorine so that those two things could come together. These guys aren't really doing anything. I could have swapped this. It disappeared there. You guys, can you hear me now? Yeah, you got me? Okay, yeah, I don't know what happened there. You know what, I'm gonna open my door. For whatever reason, my internet is unstable right now. Okay, so we've got these spectator ions that, you know, really could be swapped out with something else. They're not involved in the actual precipitate equation. They're just sort of delivering the stuff. So if I kind of take those out of the equation because they're not really important, like sort of just, you know, put a slash through them. What I end up getting is Ag plus the Cl minus, and both of those are aqueous. When they come together, we get a solid AgCl. That's the important thing in the precipitate reaction. And that would be known as our net ionic equation. So we've got our molecular equation, the complete pain in the butt ionic equation, and then we've got the net ionic equation. And that net ionic equation is giving you or giving the reader just information on what's important for our precipitate reaction. So you will need to be able to do all of those. Let's try one. The slides don't really have one. Hold on one second. So I'm going to give you an equation, and I want you to write, I'll give you the molecular. Let's do Na2SO4 aqueous plus SrCl aqueous gives us 2NaCl aqueous plus SrSO4 solid. So this is the molecular equation. I want you to give me the complete ionic equation, and then I want you to give me the net ionic equation as well. The net ionic equation will be easier to come up with once you've gotten the full complete ionic. Make sure that you break ions apart appropriately. So, you know, if you've got two of them, make sure you're putting 2 in front of there. I'll give you all a couple minutes for that. Okay, so a couple people with cameras on are kind of just staring at me, so I'm going to start going over it. Let's see. So When we're breaking these things apart, we want to break them up into their ions. So this one right here, I've got a sodium ion, which is Na+. I have to put the charge on, and it's going to be aqueous. And the sulfate ion, SO4 with a 2- charge, and this is also aqueous. Now, how many sodiums do I have? I have 2 sodiums, so I'm going to put a 2 in front. I'm not going to put the 2 down here in the corner because is sodium a diatomic molecule? No, and it's not a diatomic molecule as an ion anyway. So we pull the 2 out into the front, saying 2 sodium ions, 1 sulfate ion. That is going to combine with one of these strontium ions, which has a 1+ charge. So I need to write the 1. And this is aqueous, plus the chlorine minus charge, which is also aqueous. So these are all of the ions present. Oh, this isn't balanced. Hold on, I think I wrote something wrong. That strontium is supposed to be a 2+. Yeah, sorry, my bad. Yeah, this should be a 2. Sorry about that. So this should be a 2+. Yeah, sorry if I drove you crazy there, trying to figure that out. All right, strontium is a 2+, 2 chlorines with a minus charge, and these are also aqueous. So this is what we have going on. We have 2 sodiums floating around, 1 sulfate ion floating around, a strontium, and 2 chlorines. So now these things are going to bump into each other, and my potential products are sodium chloride and this strontium sulfate, which this is the solid. So I have to break this up. So I have 2 Na+, aqueous, plus 2 chlorines, which is also aqueous, plus the precipitate, SrSO4, solid. So yeah, it's kind of tedious. You do need to put the aqueuses in for everything that's aqueous. You do need to put the appropriate charge in. Now for the complete ionic equation, you're going to want to take out anything that is a spectator ion. So what is the same on both sides? So I have 2 sodiums here, and I also have 2 sodiums floating around here. They're not actually doing anything in the reaction. I have 2 chlorines and 2 chlorines. The only thing that's doing anything is the strontium and the sulfate. So we can write an equation just using those. Leave everything else out. I like to write the metal first and then the non-metal. So I'm going to write that strontium first. So Sr 2+ aqueous is going to come together with sulfate, SO4, 2-, which is also aqueous. But when they come together, they form a precipitate, Sr SO4 solid. And that would be the net ionic. Okay, so definitely are going to want to be able to do those 3 for your precipitate reactions. Let's look at some other types of reactions. So the next one is an acid and base reaction. Precipitate reaction, we get something aqueous and something aqueous, and we get a solid that comes out of it. In an acid-base reaction, you're going to have an acid combining with a base, and your products are always going to be a water and a salt. You need to be able to come up with the water and the salt. Water is easy. It's always H2O with a liquid. The salt will be whatever is remaining. So how are you going to classify acids for right now? If it has an H sitting in the front of it, like this, HCl, HBr, H2S, anything where that H is sitting in the front, that's an acid. A base has an OH. at the end of it. Okay, our definition of acids and bases will get a little more complicated towards the end of the semester, but for now, that's your go-to. Now, if one thing has this H plus and another thing has this OH minus, those two things can combine together to form your water. So this and this come together, and then what's left over is the metal and the non-metal, and those just form a salt. And by salt, I mean something that's ionic. All right, salt is a general term for a metal-non-metal combination. In this case, it's actually table salt, but we could have something else. If we were to write out the complete ionic equation, right, and we were to break all these things apart into their ions, the only thing that's actually doing anything is this and this to form this, right? The acid is coming together with the base to form neutral pH of water. How do you neutralize an acid? You put a base in it. How do you neutralize a base? You put an acid in it. The sodium, the chlorine, those are just spectator ions. They're just delivering the H and the OH, which is the important thing. So the net ionic equation for an acid base is always this. This is really what's happening in every neutralization reaction. An acid of some kind is forming with, coming together with a base of some kind to produce liquid water or neutral pH. Here are some acids. Here are some bases. Notice how the H is sitting in the front. That's going to be your definition of an acid for right now. Notice the bases all contain OHs. Some of them have two OHs. Some of them have two H's, right? These are diprotic acids, two hydrogens. These bases have two OHs. So let's see. I'm going to give you two things. No, you don't want my email. I want you to tell me what the products are. And then write the net ionic equation for it. You don't have to do the complete. You can just do the net if you know what it is. HBr is coming together with MgOH2. I want you to write the products. I also want you to balance the equation. This is aqueous. Let me clean this up. This is not. Let's make this HBr aqueous. It's coming together with MgOH2 aqueous. I want you to give me the products. I want you to balance it. And then I want you to write the net ionic equation as well. So what's the net? I'll give you all 2-3 minutes for that. Okay, so, you know, if you were given something like this on a test or homework, you'd have to like be able to identify that this is a neutralization reaction. And how would you do that? Well, you'd see that this is an acid and this is a base. If you can't identify that that's an acid and that's a base and that's what's going on, it's going to give you it's going to be difficult to figure out what the products are. If you're like, okay, this is an acid, this is a base, the products are always, the first one you can always write out is water. I can always write that because it's neutralizing. All right, so it's a liquid. Then I need to take whatever is left over and mix it together. So I use the H and the OH. The other products are going to be the magnesium and the bromine. Now, magnesium has a 2+ charge and bromine has a -1 charge. So the correct formula is MgBr2. And this thing is aqueous. This is just sort of acting as, this is also a salt. So I have to balance it. So I'm going to put a 2 here and a 2 here. That'll balance me out. Now to write the net ionic equation, well, anytime you have an acid and base, the net ionic equation is going to be H+ aqueous plus OH- aqueous gives me liquid water. I mean, you could go through the process of breaking each of these up and you will get the complete ionic equation, cut the spectators off, and then you'll end up with this. Well, you'd really end up with 2 of these and 2 of these, produce 2 of these, so you can get rid of the 2s. That's why I only wrote it as 1 and 1 and 1. So when you have an acid and a base, you get water and a salt. You want to be able to produce those. Expanding on acid-base reactions, sometimes we can get a gas evolution reaction. Usually they're acid and base reactions. I'm not going to test you a whole lot on these. You just need to kind of really be able to identify that it's a gas evolution reaction. So we've got, usually it's an acid combined with some sort of base or thing that's behaving as a base. You get water, you get a salt, and then you get a gas. Really how you would know that this is a gas evolution reaction, like the extent that I want you to go with is this is aqueous, and one of your products is a gas. So you know that a gas is coming out of these aqueous solutions. You'll be good with that. Okay, oxidation reduction reactions. For now, this is just going to be sort of a concept-based thing. I'm not going to have you guys like have an equation and identify it as an oxidation reduction. I just want you to know like the concepts of it. So in any reactions that we classify as oxidation reduction or redox reactions, it's when there's some sort of transfer of electrons happening. So one thing is gaining electrons, another thing is losing electrons. This is why things rust. It's why things oxidize. It's how you bleach hair. It's how you produce electricity in a battery. And a lot of times redox reactions involve a substance combining with oxygen. So in a redox reaction, you have both reduction and oxidation happening. One thing is being reduced, one thing is being oxidized. Here's some helpful mnemonics for how to remember what they mean. Oil rig, oxidation is loss. So the thing that's being oxidized is losing electrons. Okay, the thing that's being reduced is gaining electrons. So if one thing is being oxidized, it's losing electrons, another thing has to be gaining those electrons. They can't just be floating around. Here's another one, Leo the lion goes grr. Loss of electrons is oxidation, gaining of electrons is reduction. Oxidation and reduction must occur together. If one substance loses electrons, another has to gain it. And that's all we're going to say for oxidation reductions for right now. I'm not going to have you identify oxidation reductions or what's being oxidized and what's being reduced in an equation. Just know the concepts of it. Some things, substances usually that react with oxygen are redox reactions. Metals reacting with a non-metal tend to be redox reactions. One substance transferring an electron from another. Combustion reactions, which we've kind of already talked about a little bit, are a type of redox reaction. So we can put combustion reactions sort of underneath the category of redox reactions. This is where you have some sort of hydrocarbon. It combines with oxygen. It produces energy, CO2, and H2O. Those are always going to be your products. Just like an acid and a base will produce water and salt, a combustion reaction will produce CO2 and H2O. So here's sort of a flow chart of all the chemical reactions. We've got our precipitate reactions, our acid-base reactions, our gas evolution reactions, which a lot of times are acid-base reactions, and our oxidation reduction reactions, which can include combustion reactions. So I'm going to give you an oxidation reduction. I want you to write the reaction for me. So write a combustion reaction on there. For pentane. You're like, what is pentane? C5H12. So I want you to write a combustion reaction. Remember, combustion reactions, it's always the hydrocarbon, combine it with oxygen. It has consistent products every single time. Write the products and then balance it. All right, so for each of these equation groups, you do need to have a general understanding of them. I'm not going to have you do gas evolution reactions. I'm not going to have you do redox reactions, but I could ask you something like this, where there's a combustion reaction and you have to complete it. So a combustion reaction, the hydrocarbon may change. This first part may change, but the rest of it is the same. You're always going to combine it with oxygen, and oxygen is O2. And you will always produce CO2 and H2O. There's a consistency to it, okay? So this could change, but the other things will stay the same. Now you have to balance. So you have carbons, hydrogens, and oxygens. We have 5 carbons, 12 hydrogens, 2 oxygens. And on this side, I've got 1 carbon, 2 hydrogens, and 3 oxygens. Remember, when you're balancing for combustion reactions, do carbon first, then do hydrogen, then balance oxygen at the end and hope that it like works itself out. So carbon, we have 5 on this side. So let's get 5 on this side. So I'm going to put a 5 in front of it. Hydrogen, I have 12 on this side and I need 12 on this side. So I'm going to put a 6 here multiplied by the 2 to give me the 12. My oxygens have shifted. So I've got 10 oxygens here and 6 oxygens here for a total of 16 oxygens. How many oxygens do I need on this side? 16. So I can just put an easy 8 in front of there and it balances it to 16 and we are good to go. So just from knowing the hydrocarbon and the fact that it's a combustion, you should be able to write this. If instead of it was pentane, I said it was methane. Methane, and I would give you the thing, CH4. You could write an equation for the combustion of methane because again, it's the same system. CH4 is going to combine with oxygen to produce CO2 and H2O. Balance your carbons, those are good. Balance your hydrogens and balance your oxygens. You guys seeing how it's sort of consistent even though the hydrocarbon changes? Okay, great. Let's see what else we got in here. We'll make sure we get through everything before the end of class. So this is one way of classifying chemical reactions, right? Is it one of these things? There's another thing we can do. We can also classify chemical reactions by what the atoms themselves are doing. So these definitions can get layered on top of the previous ones. So we can be a precipitate reaction that is also classified as a double displacement reaction, okay? So you can give them both. So what are the atoms doing? You can think of this as sort of like a dating situation. So a synthesis or a combination reaction is when two people get together. So we've got A and B and they come together to form AB. A decomposition is like a breakup. So we have a compound AB and it, for whatever reason, breaks apart into A and B. These are generic elements. A single displacement is like, it's kind of like a home wrecker situation. So there's BC, there are a couple, and A comes along and A is looking a little bit more appetizing than B. So C boots B and it takes A, all right? It's displaced it. But this is a sort of a conservative home wrecker situation. So C is not going to end up with another nonmetal. It's going to end up with another metal. Okay, so only displacing metal for metal. Double displacement, again, this is like our swinger situation. So we have a couple here and a couple here and they flip-flop partners. Again, it's a conservative swinger situation. So A is going to go with D and C is going to go with B, or the metal is only going to swap with the other metal. So it'll be metal, non-metal, metal, non-metal as our products. This is very similar to the precipitate reaction, right? It actually is a precipitate. The precipitate reaction is a double displacement. Let's look at a couple individuals. So here's the synthesis of sodium chloride. We have sodium, which is a metal. We have chlorine, which is a gas. And we can put them together and we can form sodium chloride, or the gas will actually react with the sodium. And we get table salt, two things coming together. The decomposition of water. So I have water, I can put it in this simple apparatus with a battery and I can actually separate out the hydrogens and the oxygens. So we had a unit and now they've broken apart. Here is a single displacement. So I've got copper chloride, and these are in an aqueous solution. And then I've got this zinc bar. And what I do is I stick the zinc bar in and the chlorine is more attracted to the zinc than it is to the copper. So we will start to form zinc chloride in solution and poor copper ends up getting deposited on the zinc stick. So the zinc and the copper flip-flop spots. Double displacement reactions. All of the precipitate reactions are double displacement. A lot of the acid and base reactions are double displacement. Gas evolutions tend to be double displacement as well. So these are where we just have a flip-flopping of partners. So if I go back, they don't really give an example, but if I go back to For instance, here, this we would say is a double displacement. One thing is bonding with something from the other and vice versa. So we get two new compounds, all right? Same thing with all those precipitate reactions. Those are all double displacement reactions. They're all flip-flopping partners. So you want to be able to lay that on top of the definitions. So let's see what we've got going on here. Where was that sheet? I don't know if I have it. Where we were looking at those balancing chemical equations. Chapter 7. I don't know why that isn't labeled. Okay, so we balanced these a good amount of these already, but just as far as like classifying them, so this first one here, we would say that that's a synthesis reaction, right? We're synthesizing this compound from these two individual things. This next one here, we would call that a decomposition. We've got a compound that then breaks apart into simpler things, components. This right here, this is a single displacement. This is that home wrecker situation, right? We've got a unit, the fluorine comes along and boots the chlorine. And now we've got a new compound and the other guy's by himself. This would be synthesis. This here is swapping partners, double displacement. This here is, I would just call this a combustion reaction. All three of these are combustion reactions. They're not really swapping in that traditional sense. This is sort of splitting into both of them. So yeah, I would just say we would go with combustion for those. This one down here is a double displacement. Right, so you want to be able to classify them by what the atoms are doing. So we've got, this way of classifying, and then we can also layer this on top of it. And that is it for this chapter. So any questions on what we've gone over today? You guys will have labs due at the end of spring break. Okay, so think of this time as like a very long weekend, and you will have a lab due on April 4th, I believe. But you won't have anything this weekend. I will be on vacation. What's up, Elizabeth?
Sorry, could you back up and go over the spectator ions again? Because you were fading out on that.
Oh, yeah, totally. So just kind of conceptually what's going on with the spectators? Okay, so what's happening with the spectators is you've written your complete ionic equation, right? You've broken up everything into its aqueous ions. The things that are the same on both sides and they aren't involved in the equation are known as the spectators. So do you see here how it's NO3 by itself, and then over here it's also NO3 by itself? It means it's not involved in the reaction. Same thing here, we've got the Na plus and the Na plus. They aren't actually doing anything. That's what we classify as a spectator ion. If you look here, do you see how Ag plus is by itself here, but over here it's in a unit? It has changed in some way. That would not be a spectator ion.
Okay, so let me just make sure I got this. So in that equation that we did where it was what is it? HBr? How do you say that as an acid? Bromic acid or?
Yeah, hydrobromic acid.
Hydrobromic acid plus magnesium hydroxide, and then the net ionic equation, we wrote down what formed the water, right? Mm-hmm. Correct. So that was because we're taking the hydroxide molecule and it's being broken apart.
Here, I'll show you. Let's just do the complete ionic for it, and then we'll do the net just so we can get it. So Mg Br2 aqueous. Okay, well, let me balance it. I'll put a 2 here. 2 here. Okay, so if I was to, and this is aqueous, sorry, and this is aqueous. So if we do the complete ionic equation, I have to break up everything. So that's 2 H pluses, and those are aqueous, plus 2 Brs, which are also aqueous, plus a magnesium, so an Mg2+, which is aqueous, plus 2 OH minuses, aqueous. Okay, so there's 2 of these floating around, 2 of these floating around, 1 of these, and 2 of these. Now, we will produce the liquid water. We keep that together because anything solid, liquid, and gas, we just keep as a unit. They're not going to break apart. And then we've got this over here. So I've got a magnesium with a 2+ charge. That's aqueous. And I've also got my Br minus, which is aqueous, and I've actually got 2 of those. You good with that, Elizabeth? Okay, so now as far as what are the spectators, it's the things that are not involved. So there's a Br over here, 2 Brs and 2 Brs. They're not, they don't change. Also the magnesiums, those don't change. So the only thing that's left is this, this, and this, which would produce 2 H pluses. I'm not going to write the aqueuses. 2 OHs gives me the 2 liquid waters. And again, we can just sort of cross the 2's out and it gives us that generic neutralization. So it doesn't really matter like what this is and what this is, it will always end up giving you this as the net ionic. Like what instead of Br, what if we did Hi? And instead of magnesium, we did calcium. Those are still going to be the spectators, and this will still end up being the net ionic at the end. Because these things are just delivering what's important, which is really the H and the OH in a neutralization reaction. Questions?
I think I understand that better. Thanks for going over that again.
Okay, yeah, no worries. Anyone else? I'm going to let you know I am going to be on vacation next week, and I will be like totally gone. So I will not be on email. So the last time I'll be answering emails really until Monday of the day we get back will be this Saturday. So if you want to work on labs and stuff and get them done early, feel free to submit things to me on Saturday. Otherwise, yeah, I will see you guys on the 5th. Monday the 5th. If you have any individual questions, feel free to stay around. If you need me to go over with something, again, individually as well, I can. Otherwise, have a really awesome spring break. Enjoy the break. And then when we come back, we're just going to hit it and get it done. We'll be in the last little section here. So, bye, guys.
I have a question. So wait,
What's up, Carrie?
wait, spring break is like the 29th of March?
Yeah. Yeah.
Oh, shoot. I thought it was the next weekend. Okay.
Well, it better be the 29th. We have a house in Charleston that we rented. Yeah, it's the 29th to the 4th.
Oh, no. Okay. Okay. Perfect.
Okay.
Great. Well, thank you so much.
Yeah. Enjoy.
You too.
Bye.
Bye-bye.